Okay, welcome to the Matrix Factorization 2 session. The first speaker of the session is Qing-Yan San. The title of his talk is Convolutional Imputation of Matrix Networks. Okay, please.
Hi, everyone. It's my honor to present my work with two of my advisor and my collaborator. So I'm Qing Yun. I'm a fifth-year PhD at Stanford. And this is a work with Mengyuan Yan, which is also a PhD at Stanford, and two of my advisors, David Donahoe and Stephen Boyd. So today I would like to talk about a work we did on tensor completion, and we have a new notion called matrix network. So what is a matrix network? Intuitively, you would think it's just a tensor, right? Since you have a bunch of matrix forming a network. So in this talk, I want to show that we need to respect the structure in data. For example, for a tensor, you might think it as just a linear algebra object, but there is geometric structure, and exploiting this geometric structure would help. So here, the first example of a matrix network is literally a tensor. Like we saw here is a lot of different slices of medical images. And there is spatial structure between this medical image in the sense that they are different slices of the same brain, and they have like a connection between them. So you don't want to perturb the order of these medical images. A more extreme example would be a video, which is a matrix value time series. So here, a man is playing tennis. So his action is actually a sequence of continuous action, and this time aspect is very important in video analysis. And if we treat them as a sequence of static tensor, we would lose this information. So far, we still saw a bunch of tensors with maybe a time direction. So why do we bother to call it a matrix network? So another example, in Facebook, we know in Facebook everyone has their preference and stuff, and the Facebook may already record all your personal behavior, like all your privacy and stuff. And at the age of deep learning, what would they do? They would do a vector embedding or matrix embedding, literally, because you have so many actions. They would map all your like personal characteristics to a feature matrix. So in the view of Facebook, the entire social network is a giant graph with a lot of feature matrix on top of each person. So mathematically, you can think of this as a matrix-valued fiber bundle on a network, which is our social network. And we have a base space, which is this social graph, and we have a matrix-valued fiber. So mathematically, we can just define matrix network as a matrix-valued function from the node of graphs to matrices. So one inspiration of this definition is from a beautiful connection between differential geometry and physics. We all know that like a lot of our natural forces, like, for example, like electronic magnetic field, is actually a bunch of gauge field, and they can be represented as like vector bundles on top of our space-time. For example, here is an example where we are looking at the mathematical structure of our space-time, like as a one-dimensional line, of course, because we can only show two-dimensional stuff on the screen. And on the y-axis, we're looking at internal space on top of each point of space-time, which is a U1 abelian group. And you can think of the magnetic field in our life. In fact, we are experiencing magnetic field right now since we are all using our Wi-Fi. They are like a map from the base space to the space of fiber bundles, which is like on each node you have a map to the U1 group. So there is a very famous story that Zhening Yang actually discovered what they are working on as gauge field is in fact being studied by mathematicians in the same time in a very different name called fiber bundles. So in geometry, the entire object with a base space and fibers on top is called fiber bundle, and the base space is often a manifold. In physics, it's what we call field, and the base is also manifold, which is space-time. But in the age of data science, we live in discrete world, so the notion of manifold is not the most fundamental notion, I would say. So here, the most natural way to model this spatial relation is by a graph or network. So we call our base space a network and call our fiber bundle a matrix network. So why do we take so much effort to generalize something from tensor to matrix network? I'll show you an example, which is imputing missing matrices, that if you think of them as tensors, it's impossible. But with a new geometric point of view, you are able to do more. So let's think of the setting in the Facebook example. This is a real graph from Facebook released online. And all these nodes are, in fact, different users. And if I'm Facebook, I want to make money by ads, by recommendation. So I need to have very good information about everyone. But for some users, they are heavily addicted to Facebook, so they have a lot of behavior information. So we assume their feature matrix is well observed. And for example, here some users may have 50% of all the features required observed. For example, they may fill in all their nationality, they are male or female or whatever. And for some users, it's just a cold start. They just registered and they haven't filled in any information. So for those new users, how do you give them recommendation and how do you serve them ads? You don't want to treat them as just any average person. You want to exploit their social structure and recommend them things that they might be interested in according to their social relation. So mathematically, it's like a graph, and some of matrix are partially observed, and some of the matrix are completely unobserved. Another example is MRI. So in MRI, the MRI is a good example for all this sparsity and matrix completion because it has very good structure. But in reality, MRI is not just a vector in computer sensing. It's actually a tensor or a matrix network, since you have multiple slices of medical images, as I was showing before. And let's consider a setting when for a lot of the images, you don't have any observation. And for some of the image, you have a full observation or just a partial observation. For example, you only observed bottom 20% of the image, and your machine may not be that reliable, so didn't get the top half. And with matrix completion, if you think of every image as a vector and stack them together as a matrix, you have a lot of columns. That entire column is missing. So in the traditional matrix completion world, this is impossible. But with our method, we can see we have most of the features of our oracle image recovered. So under this new observation model for missing data, the vanilla matrix completion method always fails because the new setting has entire column missing. And we might think, okay, let's think of it as a tensor. And every image as a matrix, you stack them together as a big tensor. So you can do tensor completion using your favorite CP structure or whatever tensor factorization structure. However, you have entire matrix slices missing, and all this tensor completion structure needs to assume you have random sampling. So each entry is missing with, like say, Bernoulli random variable. So this deterministic full slice missing scenario is also impossible for tensor. So what's the problem with the method matrix completion and tensor completion? They didn't exploit the global structure between these matrix. If you look at the MRI image, they have this spatial relation. If you exploit this spatial relation and you assume the medical image you get for different slides don't change violently since they are from the same tissue, then you are able to actually use global information to recover the entire tensor. Okay, so what's the best way to exploit geometric information? So one idea we might have is do Fourier transform, which is a very typical trick in mathematics. So in the case of like a network, you have a weighted adjacent. Oh, sorry. You have a weighted adjacent matrix of a graph. So graph may be a weighted graph or just an unweighted graph. So here, for simplicity, we assume it's an undirected graph. Then we can define our graph Laplacian or like normalized graph Laplacian here because we normalize the degree of the graph. Then we can define the eigenproblem, which is a typical trick in spectral graph theory. Let's see here, L is our normalized Laplacian, and we define the eigenvalue to be E, which is a diagonal matrix, and our eigenvector to be U. So what is this U? The eigenvectors. Let's look at the simplest case when our graph is literally just a 1D grid, which is the case for the video when it's a time series, or when it's the case of this MRI image when we just have a 1D spatial scan. Then the eigenvector U is in fact the discrete Fourier transform that we studied in high school. So one column of this matrix U would be just sinusoids. In general, when we have a weighted graph, Fourier transform is not the right notion that respects the geometric structure of graph. So we define our graph Fourier transform to be the transform made by let U act on our matrix. For example, here we define A hat to be the graph Fourier transform of A by multiplying this U matrix on the base space. So notice here that AI is actually a matrix, but UKI is actually a scalar of the unitary matrix. So here we are just doing linear combination of a bunch of matrices. So in the Fourier space, we can assume some structure that would help us to do the completion task. So one structure I decided to use here is a low-rank structure in the Fourier space A hat. So mathematically, we define our observation model to be like A is the inverse Fourier transform of A hat, and we only observe a fraction of matrices A in A. We call the observed part A omega, and the P omega would be the observation sampler, which is a matrix that sum of the entry is just a 0, sum of entry is 1 as a projection. And we assume all the matrix in Fourier space A hat K are all less than rank K, or rank R. So is this a reasonable assumption? Let's do a sanity check. So look at our MRI example. If we do Fourier transform by compute linear combination of these images, and then we do SVD on them, we see the singular value of these images actually decay super fast. So they are like 256 by 256 matrix, and almost the first 20 singular value is enough to capture all the variance. So in fact, this low rank assumption makes sense. So if the low rank assumption makes sense, then we can design an algorithm to solve the problem. So here is a iterative imputation algorithm. So we can come back to this later, but you can just get a feeling of it. It's a convex problem that we observe this A omega, and we want to find M hat so that M hat is the minimizer of this convex objective L lambda. And we can do something like analog of lasso path. We start with a sequence of decay parameter lambda 1 to lambda c. And we just run the first iteration with lambda 1, use that as the warm start for the second problem. And in the end, when our lambda c is very small, our solution is very close to the solution of the original observation model here. So one of our main theorem is actually about this limiting convex formulation. When we minimize the sum of the nuclear norm for this Fourier matrix, we call it M hat, subject to linear constraint, A omega equals P omega U star M hat. So we reduce the problem to a tensored version of kind of compressed sensing problem. And you would know, like with compressed sensing type problem, we have a lot of technique to actually show there are exact recovery. And here, we get one of this theorem where the most interesting part is our result only depend on the average sampling rate, which is the average amount of entries you observe. So it doesn't really depend on whether you sample randomly, which is the easy case, or you sample only a fraction of slices, which is a very hard case for tensors. And numerically, we can just do synthetic experiment by Gaussian low-rank matrix. And we see there is a relation between the undersampling ratio, which is the amount of total entry observed, and the relative MSE. So the more interesting plot is this. So we do like 100 times of the same experiment, and we see the success probability is very sharply separated between 0 and 1. There is only a color of boundary, which is the part that you have a fraction probability to recover the problem. So this is an important phenomenon in this field called phase transition. And here is another example where we have a simple temporal image of our synthetic heart. And we miss entire consecutive frames, which is, say, we take a video and at like a certain time period, our machine just fail and it come back on time. So this is extremely hard because it's missing consecutive, and you can't just linear interpolate images to recover them. And we show that our method is much better than the tensor completion method, especially on those cases when you don't have observation. Like the tensor completion method just blow up, and our method are still able to get reasonable relative MSE. Okay, so to conclude, the big takeaway message is actually our modeling framework. So this new notion of matrix network might help you when you have a problem that is tensorial. You would think, is there spatial structure and symmetry in some of the dimensions? If there is, then you should exploit those structures. So we demonstrate the advantage of our modeling framework by this tensor completion, or like imputation task under our sampling model, which is missing like several slices of the entire tensor. And the structure we we assume is low rank after graph Fourier transform, which is basically you have a structure under some incoherent domain with respect to observation. So the principle of compare sensing actually works, and you are able to use the structure in global information to recover your observation. And we have a very efficient imputation algorithm, which you can come to my poster and get a sense how to implement it. And we have like a strong theoretical guarantee with phase transition. So if you have any question, feel free to come and talk to me at my poster at 70. Okay.
Okay, thank you very much. So we are running up time, so let's go to the next speaker directly.